Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual landscape of the early 20th century, physics stood at a precipice, the grand edifice of classical mechanics, a bastion of deterministic certainty for over 2 centuries, began to show profound structural fissures. It was in this charged atmosphere, a moment of both supreme confidence and creeping doubt, that Ludwig Boltzmann's monumental work, the 2-volume Lectures on Gas Theory, received its English translation in 1904, following its German publication in the Warshaus in 1890s. This work was far more than a mere textbook. It was a definitive testament of a brilliant and besieged mind, a masterful synthesis of the atomic theory of matter, and a courageous, almost desperate, defense of a probabilistic worldview that many of his most esteemed contemporaries found philosophically abhorrent. Boltzmann's lectures represent the absolute zenith of classical statistical mechanics, a theoretical structure of immense power and elegance, whose mathematical armature and conceptual depth provided the indispensable foundation for the quantum revolution, even as it embodied the very intellectual battles that would define the end of the classical era. To appreciate the radical nature of Boltzmann's project, one must first survey the terrain he inherited. By the late 19th century, the laws of thermodynamics were well-established pillars of physics. The work of Carnot, Clausius, and Kelvin had yielded a powerful phenomenological theory centered on the conservation of energy and the inexorable increase of entropy. Yet, a chasm remained between this macroscopic science of heat and work and the microscopic world of Newtonian mechanics. Rudolf Clausius had himself taken a crucial step with his concept of disgregation, a measure of the dispersal of a system's molecules, hinting at a connection between entropy and molecular arrangement. It was James Clerk Maxwell, however, who provided the first truly statistical tool, developing a probability distribution for the velocities of molecules in a gas. Maxwell demonstrated that the collective properties of a gas could emerge from the chaotic, random motions of its constituent parts. Boltzmann, a profound admirer of Maxwell, took this conceptual seed and cultivated it into a vast theoretical forest. His ambition was to derive the second law of thermodynamics, with its unidirectional arrow of time, directly from the time-reversible laws of mechanics governing atoms. This quest to reconcile the reversible micro-world with the irreversible macro-world became his life's consuming passion. The Lectures on Gas Theory is the grand architecture of this quest. The work is a model of pedagogical clarity and logical progression, guiding the reader from the simplest assumptions to the most profound consequences. In the first volume, Boltzmann constructs his theory for ideal gases composed of monatomic molecules. Here, he introduces his most formidable and famous creation, the Boltzmann transport equation. This integral differential equation is a masterpiece of physical intuition. On one side, it describes the smooth, deterministic change in the particle distribution function within a 6-dimensional phase space of position and velocity, accounting for the drift of particles and the influence of external forces. This is the classical, Newtonian aspect. On the other side, an integral term, the collision integral, describes the effects of binary molecular collisions. This term represents the stochastic, probabilistic heart of the theory, calculating the rate at which particles are scattered into and out of a given velocity element. It is a brilliant fusion of deterministic flow and statistical chaos, an equation that governs the evolution of probability itself. From this single equation, Boltzmann derives the Maxwell velocity distribution as its equilibrium state and, most critically, its H-theorem. He defines a quantity, h, given by the integral of the distribution function multiplied by its own natural logarithm across all velocities. The H-theorem demonstrates that, for any initial state of the gas, the value of h can only decrease over time, reaching a constant minimum at equilibrium. By identifying this quantity h with the negative of entropy, Boltzmann had seemingly achieved his goal. He had derived the second law of thermodynamics from the mechanics of molecular collisions. The true revolution, however, lay in the philosophical interpretation that Boltzmann attached to this mathematical result, an interpretation that occupies the core of his later arguments. He proposed that entropy was fundamentally a measure of probability. The famous formula, S equals k logarithm of W, where S is entropy, k is the universal constant, that now bears his name, and W is the number of distinct microscopic arrangements of atoms, or microstates, that correspond to the same observer or macroscopic state, or macrostate, was the ultimate expression of his vision. This reframing was shocking. The second law of thermodynamics, previously viewed as an absolute, inviolable law of nature like gravity, was demoted to a statement of overwhelming statistical likelihood. A system, left to itself, does what is most probable. It evolves from less probable, more ordered states to more probable, more disordered states because an astronomically larger number of microscopic configurations correspond to the latter. This probabilistic conception of reality was anathema to a powerful philosophical movement of the time, the positivism championed by Ernst Mach and the energeticism of Wilhelm Ostwald. For Mach, science should concern itself exclusively with observable phenomena. Since atoms were unseeable, they were metaphysical constructs, and any theory built upon their hypothetical existence was suspect. Ostwald argued that energy, its transformations, was the sole reality of the physical world. For these thinkers, Boltzmann's mechanical model built upon a foundation of imaginary particles was a speculative fantasy, a step backward from the clean, phenomenological purity of classical thermodynamics. This profound opposition forced Boltzmann to defend his theory against a series of brilliant and deeply troubling paradoxes, and his responses, detailed throughout his writings and implicitly underpinning the logic of the lectures, reveal the subtlety of his thought. The first was Loschmidt's reversibility paradox. Joseph Loschmidt pointed out that since the laws of mechanics are time-symmetric, if one could instantaneously reverse the velocities of every molecule in a gas, the system should retrace its path, evolving from a high-entropy state to a low-entropy one, in direct violation of the H-theorem. Boltzmann's defense was statistical. He conceded that such a reversed state was mechanically possible, but its occurrence was fantastically improbable. A system almost always evolves towards a more probable state because the paths leading there vastly outnumber the paths leading to less probable states. The second major challenge came from Ernst Zermelo, who armed himself with Poincaré's recurrence theorem. The theorem proves that a close, finite mechanical system will, given enough time, eventually return arbitrarily close to its initial state. This implied that entropy must eventually decrease, making the second law a cyclical phenomenon. Boltzmann's response was a masterstroke of scale, the Poincaré recurrence time for any macroscopic system, such as a mole of gas in a box, he calculated, was a number so vast that it dwarfed the age of the universe by many orders of magnitude. The objection, while theoretically sound, was physically meaningless. The second law holds true for timescales relevant to any conceivable experiment or cosmic epoch. The tragedy of Boltzmann's story is that the ultimate vindication of his atomic worldview arrived too late for him to witness. He ended his own life in 1906, despondent from the relentless intellectual opposition and his failing health. 1 year prior, a young patent clerk named Albert Einstein had published a paper on Brownian motion, explaining the erratic dance of pollen grains in water as the result of collisions with unseen water molecules. Einstein's theory provided a method for calculating Avogadro's number, and the subsequent experimental work of Jean Perrin provided stunning empirical proof for the existence of atoms, silencing the energeticists and positivists for good. The foundation of Boltzmann's lectures was proven solid. More profoundly, the statistical methods he had pioneered became the essential toolkit for the new physics. Max Planck, initially a skeptic of atomism, found himself unable to solve the puzzle of blackbody radiation using classical thermodynamics. In what he later termed an act of desperation, he adopted Boltzmann's statistical approach, applying the formula S equals k logarithm of W to a system of oscillators. In doing so, he was forced to quantize energy, introducing his famous constant, h, and unwittingly launching the quantum age. The probabilistic universe that Boltzmann had envisioned, a universe governed by statistical laws, became the bedrock of quantum mechanics, while a more abstract and general ensemble theory developed by Josiah Willard Gibbs in America would eventually become the formal mathematical language of statistical mechanics. It was a framework erected upon the conceptual ground cleared and fortified by Boltzmann. In conclusion, the lectures on gas theory transcends its role as a mere scientific text. It is a monument standing at a crossroads of history, a work that is simultaneously a summation and a prophecy. It represents the most sophisticated and complete expression of the Newtonian atomic worldview, pushing classical mechanics to its logical limits. At the same time, by introducing probability as a fundamental physical principle, it shattered the deterministic clockwork universe of Laplace and provided the essential conceptual and mathematical tools for the probabilistic reality of the 20th century. Boltzmann fought a lonely and bitter war for his atoms and his statistical interpretation of nature. His lectures served as his fortress, a meticulously constructed argument against a world unprepared for its implications. He sought to explain the old world of classical physics and, in the process, laid the cornerstone for the new one. The scientific community would eventually come to inhabit the universe he described, a cosmos whose fundamental laws are written in the language of chance and probability, a testament to the enduring power of a vision articulated with unmatched brilliance and courage in the pages of his final, great work.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.